This is part 2 of an oxidation reduction question. Go back to part 1 to find out how to solve A, and also some really interesting information about indium, vanadium, and titanium. Second part of the problem. What is the net reaction in cell Z? Well, whoa, cell Z? They didn't tell me anything about cell Z. Yes, they did. They said it consists of half cells 2 and 3. And here they've listed cell 1, 2, and 3. Now we've already drawn cells 1, X and Y using 1 and 3 and 1 and 2. Here, 1 and 3 right here. Here, 1 and 2 right here. Well, what about 3? 3 is 2 and 3. So we're dealing with indium, metal, and, whoops, no we're not. 2 and 3 deals with vanadium metal. I've got my vanadium cell drawn to make my cell Z. I've got vanadium and, of course, vanadium plus 2. You, by now, I'm pretty sure know that the chloride ion is a -1, so the oxidation number of vanadium is plus 2. That should be automatic for you. If not, go back to oxidation reduction numbers and also polyatomic ions. You've gone this far, so you're fluent in those charges. And now we've got to get cell 3. This is titanium and titanium chloride, of course, which is titanium plus 2. Matching charges. We have half cell drawing. And again, I would have done the drawing, I think, because otherwise this is just too messy, and you don't want to lose a point because you rushed. I think you can solve the problems more quickly with half cell drawings. Now, we've got the two substances here, and of course you've got your salt bridge, you've got your voltmeter, everything else. What's going to happen if we close this circuit, connect it? We're going to have a tug of war again. We're going to have vanadium plus 2 tugging on the titanium metal. We've got the titanium plus 2 tugging on the vanadium metal. Well, which one's better at getting electrons? When we look at these two, X and Y, we saw that vanadium was doing its best to hold its own against the indium plus 3. It lost by 0.84 volts. Here, titanium lost by 1.29 volts. So the titanium's not as good at holding electrons in against indium plus 3 as vanadium is. So vanadium's got to be better at reducing. Hence, vanadium must be better at pulling in on electrons than titanium. And here's my reveal. The electrons are going to be going to the vanadium. Once I know that, I can write the equation. I'm going to know that the vanadium plus 2 is going to gain 2 electrons, ripping them off this poor titanium. Titanium is taking a beating here, but no, don't worry. Titanium looks really, really pretty when it gets its oxide coatings. So here we've got our vanadium coating, growing crystals, being plated, turning into more vanadium. So this solution will be getting less concentrated. This beautiful color of vanadium plus 2 will be fading as it turns into vanadium metal. And our titanium will be doing the opposite. So that's our two half reactions, and we can write them together as one net ionic reaction. Vanadium plus 2, ripping 2 electrons off of titanium, changing it from its beautifully colored solution into that strong metallic vanadium, and our titanium going into solution. There's the net reaction in cell Z. Now, what is the standard cell potential, which uses half cell 2 and half cell 3? Well, what's going to be the voltage? All right. Well, what's the difference between those two numbers? 1.29 volts versus the indium pulling here at 0.84 volts. The difference is 0.45. So our difference is going to be a simple 0.45 volts as our answer for the standard cell potential. Another way of doing it. This is, I think, the longer way, and the method of doing it is to realize if you reverse Y, you take this around, these two reactions will add up to make our vanadium reaction. You'd have the indium plus 3 canceling out, the indium plus 3 canceling out. You'd have the indium solid canceling out, and the indium solid canceling out. And as a result, you would get this final reaction. 3 vanadium plus 2s plus 3 titaniums making 3 titanium plus 2s and 3 vanadiums. Reduce it down 1 to 1. And of course, the difference, of course, would be this reaction is reversed. So instead of being 0.84, it's negative 0.84. And if we add these two, and we still get our 0.54 volts. So that's our answer for B and C, where we determined this mystery galvanic cell Z based on what happened on X and Y, because we had the same indium and then we had titanium and vanadium. So we were able to use that as our clue. And they always give you this on these problems where if you use some logic, you can solve it. So there's our part 2. Now to the really, really complicated one that I've saved my third and best video ever for. This is going to be answering D. So tune in for the last part of this redox problem.